between.
Start to be.
So we can record it. Oh no, you idiot. What's the shit? His laptop to load, and then he's gonna connect with him to. Yeah. Did you get it? Yeah. Turn his laptop on. No, that's on. No, that is on the screen. Yeah. Oh, sorry, man. I was just doubting you. I still have like my hair dye just doesn't come on. Regardless, I think I could physically help. The last couple of socks. And even part of society. Exactly. Are you sure it's recording? Say hi. Turn it around so it like faces the border. I want to see if it makes a difference.
I can't see you, you're too black.
Oh, shut up.
You too. What the fuck? Wave high.
What did you say? The one who went to do that thing with Lionel. Yeah. They were sitting on the bench and
Okay, so this lecture is very short, and so we have covered more than half of it, so we can just do it very quickly. I should say a few words about your homework, the two ones I corrected this morning. They were generally fine. Two apparently have not delivered. I couldn't find from two of you, so keep it in mind. The two missing students. I would like you to, there's several students here who didn't take theirs. If they don't come later today, I would like, if they have any friends, that the friends could take for them because this always get lost in my piles otherwise. Another thing is, yes, there were several things, a few things on there nearly everybody forgot. Though a few ones did it well. Those who got anywhere between 80 and 90 for that question, they must have done it right. I asked you how to joint initiate, or fractures in general initiate. And some of you did beautiful illustration for me to show how they propagate and so on, which was like a plus for and so on, that's beautiful. But don't forget, if I ask you how they initiate to start to propagate, every single fracture starts from stress concentrations. They always start from stress concentrations. And in the rocks, the stress concentrations tend to be vesicles, fossils, corners, all kind of irregularities, but particularly fossils in sedimentary rocks, fossils, vesicles, grains with different properties from the hostel. So this was one thing I noticed that you didn't, most of you didn't do. So please keep it in mind, because these kind of questions I give you here are not dissimilar from what you could expect in the exam. That was one thing. Then there was another question. Let me see. Okay. If we look at the number B in exercise A, why can we have a great depth So very, very low driving stress. Some of you did this quite well, but for many there was something missing. And let me show you what was missing, because this is fundamental, because this explains in fact earthquakes. And for the practical guys here, this is related to hydraulic fracturing and these kind of things, so you should have that clear. So what are we talking about here? Here we are fortunately talking about one very simple equation. And the equation is this one here. Tau is equal to 2 times T0 plus mu sigma n minus p t. And I wrote for many of you this equation here. Let me now go through it. Please write this down, because this might very well come in an exam. And by the way, please come on the last day of this course, which is the 27th. And that day, Matthew Thurr has asked me for this classroom for 2 hours, so the course will only be in the morning. So I strongly recommend to you to come for these 2 hours, because then I go through how to prepare for the exams. I've given you now on Moodle, I had given to you earlier, this material you need, but I always give my students advice how to prepare for the exams, which is sometimes useful if you want to have good grades, okay? So I recommend strongly you come. Here are several things to keep in mind. 1, sigma n is not the vertical stress. Sigma n is the normal stress on the fault plane. So sigma n is this one here. It's the stress that tries to keep the fault locked. It tries to keep the fault locked. Doesn't allow it to slip. That's one thing. Second thing, this PT is the total fluid pressure. It's not PE, it's the total. It has to be the total fluid pressure, because it has to lift this wall here against the total stress operating there. So it's the total fluid pressure. Now, when these two, when sigma n is equal to PT, then mu times sigma n minus PT is roughly 0. And then the only thing left is this one here. And this is commonly somewhere between, say, 4 to 8 megapascal. Here, 6 megapascal. So that fits. That fits. And please write that down. But then some of you made something I had to subtract from you for. Some of you said, then the tensile strength is the only driving force, and that is conceptually fundamentally wrong. The tensile strength is the only strength the fault has to overcome to slip. It is hindering the slip. The driving stress is always this one here, tau. So the stress has only to reach this value to cause the faulting. So this one is not causing the faulting, this is hindering the faulting, has to be overcome. So that was one thing that some of you got. But please, as you remember, you never have to learn any equations. And now you have all the equations in the pre-exam I've given you from 2011, 12, and 13 on your mobile. So they are all there with the equations. So I strongly recommend to all of you to go through these equations. Of course, only a few of them come in the exam, but you understand them, that you know how to use them and so on. So that's one thing. If you look at the other, varied a lot. Some were much better in A, and then often were not as good in B, and vice versa. So B, what mechanical types of fractures are joints? The correct answer, as most of you have, is most of them appear to be extension fractures. Most of them are extension. However, there are some joints that clearly are, or all indications are shear fractures. For example, conjugate joints. And some of you mentioned those. And the definition of a joint is a fracture that has a very small opening, and no visible shear displacement. No visible. It's a visible word, which is very important, so please keep that in mind. It doesn't mean you wouldn't see it maybe under a microscope, but in the field you don't see any displacement parallel with it. Okay, how do they form? That's number B and B, and I explained it to you. Here I wanted you to say something about the stress concentration, which is then fossils, vesicles, and all kinds of material inhomogeneities. Okay. So, number C, provide examples. When I ask you to provide examples, I usually expect you not only to say conjugate joints, columnar joints, and so on, but to try to illustrate. So one of the points I make to you when we have this preparation for the exam is the best advice I can give you is write your answers at home, those are the kind of questions you expect, including illustrations, simple ones that you can do under stress and strain in the exam, and memorize them. That's the way to do it. You can't do it for the calculation exercises, but for the definitions you definitely can. So I wanted you to show me some examples of this. Some of you did beautiful illustrations, absolutely fantastic in one or two cases. I was very, very happy with that. But it's not necessary. As you may have vaguely noticed, I'm not a very good artist myself in this respect. So I don't expect you to draw beautiful illustrations with flowers and so on. If you do, it's beautiful, but you don't need to. But just to be able to show it. Bed thickness. Well, the relationship is very simple. The relationship is very simple. If this is bed thickness, and this is frequency, the relationship is this one. The thicker the beds, for the same lithology, the lower the frequency. And many of you couldn't explain why. It has nothing to do with the tensile strength or Young's model. If there's a constant lithology, then those factors are ruled out. The reason is the same as with the layer cake. If you have layers here, and you put loading on, let's say tension to have it simple. You put tension on the loading here, on the layers here. Remember, stress is force per unit area. Stress is force per unit area. If you have a thin layer, the unit area is small, so the area is smaller that the force is operating on. Because it's very thin, of the same length, the area must be smaller, so the stresses become higher. So that's the main reason why you have much higher frequency of fractures in thin layers of the same lithology. The stresses in the thin layers are higher because the cross-sectional areas are smaller. The stresses become higher from a given force because the cross-sectional areas are smaller because they are thin. That's the only reason, or the main one. You mentioned some of you stress and so on, that was okay, and added to the story, but the main reason is very likely this one here. You have layers that are identical in all respects, except one, and they are thinner. And therefore you will have higher, if the force is constant, the tectonic force is constant, then there will be higher stresses there. So joints in fractured reservoirs. This varied a lot, but nearly no one of you, or hardly anybody, mentioned what the oil price are mainly interested in, so I repeat it here. If you are hired by an oil company, or any company dealing with fluid flow in fractured reservoirs, what they like to know is permeability. Permeability is number 1, 2, and 3. And how is jointing going to affect permeability? It depends on, are the joints strata bound? I wrote this for many of you. Are the joints strata bound, so confined to individual layers? If they are, the vertical permeability is going to be more or less 0. If they're strata bound, you remember what strata bound is, isn't it? You remember that? Strata bound is if you have layers like that. Right? Strata bound would be fractures that are confined to individual layers of strata. They are strata bound. And then the vertical permeability is going to be very, very small, which is usually good news in the oil industry, by the way. They like to have the whole super one much higher, because then there's little danger of water coming into the reservoir. So there's one thing, is strata bound, non-strata bound. 2, how commonly are the fractures arrested, stopped in their propagation? Very important for hydraulic fracturing, for example. That was number 2. Another thing you should mention there, what is the orientation? Zoe showed you from Herma a rose diagram. That's the first thing you block us. If all the fractures are trending the same, so the rose is basically one arrow, there is no interconnection, and the permeability is going to be close to 0. So the spread in direction gives you an indication of the interconnectivity, how well connected the fracture network is. So the spread in orientation is a very important thing. And the final thing I wrote for many of you, and Zoe was emphasizing, the aperture distribution. The aperture distribution. How open the fractures are. You can have a lot of fractures, if they're all filled with minerals, there's no conductivity. And in the geothermal industry, Germany, Australia, and so on, they do in fact, they put acid into the crust, which is very lots of acid, to clean out the second minerals. I will now at the end today give you other exercises, and I tell you something that is no secret at all. These exercises reflect very much what you can expect in the exam. They're very, very similar. So pay attention to them. Alright, so what Zoe did here today, I'll just briefly summarize. She has shown it very well. So we go, this is a very, unfortunately for her, this is not a very exciting lecture in the sense it's very mathematical. So it looks a little bit dry in a way. Okay, we went through this one, and this is I'm able to do, you've seen it many times. And flow with a single fracture. This was the standard cubic law. If there is no elastic effect, if there is no buoyancy, the holes on the flow here. So we went through these things and the hydraulic gradient, which is mainly used in hydrogeology, whereas in petroleum geology and volcanology we use more the pressure gradient because we assume there was elastic. This was here. The main thing is, if I ask you, which I don't think I do, no I don't do this course, the Darcy law. You probably have learned it from, you've taken some of your hydrogeology, haven't you? So in case Darcy's law comes up, the easiest way to write it is this equation here. Q is equal to KIA. And that will be of course given in your So we have these two laws of fluid flow. One is for porous medium. That is the Darcy's law. Initially Darcy did his experiments on sand. And then we have the fractured medium. But until around 40 years ago, the oil industry usually modeled all their reservoirs as porous medium. Why? Because the fracture medium is developed. Now we use, of course, the numerical models, so the real fracture. This is the hydraulic gradient, okay. Then came these two difficult equations. We have discussed them before. I've told you all because I know that some of my students don't like maths at all. You can, if they come in an exam, there would always be an option for you to drop it, not to take this part again, not to answer this question. But then you would have to answer all the others. Okay. So this is the most difficult math question I could possibly come up with an exam. It has to do with these two equations here. They are differential equations, they look complex, but in reality, they are not so complex. If we take the main one, and I'll explain it to you. I've done it before, I know, but I'll do it now once again. And show it as well, so then you have to explain 3 times. Let me show you what this really means. Let me write it first in a more simple way. Basically what we're looking at here is this thing here. Okay, we have fluid somewhere in the crust. And this fluid is going up. And if you follow me now, you will see it is in fact very easy. Just follow me for 5 minutes, then you will understand it. What we're basically saying here, first of all, we're saying Q, the volume of fluid coming out of the fracture per unit time, is proportional to the aperture in the third power. This is just the basic cubic law. We all know it now. We've used it many times, so there's no problem. There's no problem there. Then we can make it a little bit more complex by saying Q is proportional to a certain constant, B cubed. And the constant would then be all these things in front of the brackets. So W divided by 12 mu. If you write the equation now correctly, you could write it in a mathematically for you, I'm sure, and for me and all of us, much more appealing way. We can write it like that. So we write it B cubed W 12 mu. That's easy. Then comes this one here that looks partly difficult. This is a rho, and you know that before, minus a rho fluid. So this is easy. Then comes this horrible partial differential equation that looks complex. So now I write it in a more simple way. What it simply means is this thing here. This delta PE, we can write in a standard way that we all understand immediately. We write just the delta PE. And the other one, delta Z, is just delta Z. And I'm sure you find this easier to think about. And then we say, okay, what is delta Z? Well, delta Z is simply this one here. It's just the height from the source to the surface. Nothing else. Then the only thing you have to understand is how can we figure out this PE? Now, PE is, here is PE at a certain level, and here PE is atmospheric because this is the air, so PE is roughly 0 here. So what is then delta PE? Delta PE is then the difference of PE here to here. And the only thing you have to remember, and I noticed you asked Zoe about it, you did here, is what is PE? What can PE be when you rupture your reservoir? What value does it correspond to? If I have a fluid pressure here, and I'm increasing the fluid pressure, finally the reservoir will rupture. When does it rupture? What value does it reach to rupture? The same applies to volcanoes, for those of you who are in volcanology, the same for aquifers, same for oil reservoirs.
Tensile strength.
Hmm.
The tensile strength of the rock.
The tensile strength. So PE is equal to T0. That is the tensile strength. So we could have written this delta T0, but that would not be correct because T0 at the top here is the same as down there. But the pressure changes. So what happens here is that we put PE equal to tensile strength here, and we put it as 0 when it meets the atmosphere. So, to make things simple, delta PE is always equal to the tensile strength. That's all. It's always just the tensile strength. Because when you rupture here, it must be equal to the tensile strength. And when it comes up here, 0. And T0 minus 0 is T0. But if you look at it now in this way, it looks simpler. And the only snag in the exercises, and these are all solved in great detail in chapter 17 if you have access to the book. The only snag here is, as Zoe mentioned, is this strange thing here. Why does this become plus? Well, it becomes plus, first of all, because the pressure is decreasing now. That's one thing. And secondly, because when we are doing this, we always have the Z coordinate is positive down. Z coordinate is positive down. Your fluid, that's of interest to us, is coming up. So it's going in a negative direction. So this becomes minus minus and therefore plus. And that's the only error people do in this exercise usually. Well, some of them of course get a little bit of problem with the calculators of when you're doing your if you've written this down, I will not point out where the errors could come. So you remember them. Now, as I say, no one has to do this exercise in case it comes up. You can always focus on the oral exercises and the easy math. But experience shows, even if I'm making a little propaganda, those who do this comparatively complex maths in the exercise, in the exam, they usually get very high marks. Why? Because I can't lower people, and I do, of course don't want to. I can't give you anything but full if you do a calculation exercise correctly. Then you get just 100% for that part of the exam. Whereas when you write essays, I hardly ever give you, and no one really, no teacher gives you full marks, or very rarely. So what are the possible problems here? The first problem is people forget to change all the units into SI units. If I give you this one as 1 centimeter, if the aperture is 1 centimeter, which is logical way of giving it in the exercise, you have to change it into meters. And then you would get as 0.01 meter. When you do the calculations, please do not do them all at once. Separate them, because then I can at least see where you made the error if you make an error. If you just calculate everything through in your calculator, you just give the answer, I can't find out where the error is. And very commonly, this is an error. So you have to then take it 0.01 in the third power. And that becomes a very low value, of course. This one here is almost never a problem. Let's say it's a fracture a few meters long at the surface, that would be a W. Viscosity is given, no problem there. Another problem that sometimes comes up for my students, I might take an example where the rock density is, let's say, 2,400. It could be very close to the surface in a sedimentary basin or continental crust. And the density here is 2,650. So the density of the rock can be, and often is, less than the density in case of magma. And you could then say, okay, can the magma then go up? Yes, it can. Why? Because it has built up an overpressure on the way where the density of the rock is higher. And secondly, it has this thing here. This is one reason why, when you see basaltic eruptions, they're often very small, because the driving pressure is very little. There is no buoyancy helping. Buoyancy is even negative. So the only thing you need then is the buoyancy. Remember, this becomes minus, minus, and plus. I would start always to calculate this gradient here. I would start with delta P divided by delta Z. Let's say PE is, to have it simple, could be 4 megapascal. Then you have to remember to change it into 4 times 10 to the 6th. Let's say the depth is 2,000 meters divided by 2,000. And then you would have a gradient. So that's all. It looks much more complex because strictly mathematically, we should write it as a partial differential equation because it can go in all directions. But when you look at it in more classical for us, delta style, I think you will understand it's not really. So as I say, it's up to you, but I would like you to do it in case it comes up something similar, try. Now this equation applies to any kind of fluid flow, including in earthquakes, in then of course you could say, well, this one looks even more ugly, if I could use that word. And the reason is very simple. In this second case, and I will not give you that kind of exercise. The only difference is that this is not vertical, so it's inclined. And that's the reason this sign comes into the game. So, those who wanted to understand, do you think you have understood? Okay, so this is your example. This was using this exercise here. Then we have parallel fractures and orthogonal fractures. Should we try this one here? Are you in the mood? I think you're gradually waking up now. So you were not very much awake in the first hour. Do you want to use your brains to try to do this one here? So what we're dealing with here, we have something similar to what you might do in the future, I don't know. You go into the field, you measure maybe not only 40, you maybe measure 400 or 4,000 fractures. And you have a certain frequency, and you're dealing here with water, so you're in hydrogeology, and you are going to calculate the conductivity of the fracture set. That's capital K. So you have to look at the equation for capital K. This is only hydrogeology here. This is a standard exercise in hydrogeology, by the way. Those of you who want to. Any solutions? Any answers? How much would it be? You take the focal height as 1 meter and you measure exactly the way that so we did. And we just try to calculate.
I don't know the. What's it called?
Any answers?
The unit. 5.3.
5.3, 5.2. That sounds very promising.
Why don't you think it's. Yeah. That's the units.
So this is a little bit old-fashioned classical hydrogeology. Today, of course, people will put it into a computer program, but it's good for you to get a feel for what it's all about. This is hydrogeology old-fashioned. So, what does it correspond to? Well,
Divide each other.
this was 5.3 times 10 to the minus 3. Where would we find that? We had 10. We have 10 joints per meter.
Because he uses the joints per meter.
10 joints per meter. Where was this famous? 10 joints per meter. So we would look at this line here, and it would be up here. So it would be very close to the end. Can you understand how I read off this? I go up this diagonal line with 10 joints per meter because we have 40 per 4 meters, okay? And then I find out, given the amplitude here, what kind of conductivity I would expect. And it turns out to be between 10 to the minus 2 and 10 to the minus 4. So it's roughly what we got. So that fits. Theoretically, an observation lead, this would fit. Then you can expand it. You're not going to do calculations in that direction. You can take orthogonal joint systems like these here. I've shown here a typical one. If you work ever in some of the dry areas in the world, they have some of them basaltic lava flows. And then you might have the situation here. For example, in Libya, in the central part of Libya, there's a huge basaltic lava pile of field, and of course they don't have very much water there. So this would be one way to calculate the potential. This is an orthogonal joint system in Norway. Let me see what you remember. Can I extrapolate this joint system offshore Bergen, west of Norway? Can I extrapolate this to 1 or 2 kilometers depth? Which joints might not be found at 2 kilometers depth?
Extension.
As you know, Norway is in the north, and the coastal Norway was covered with ice, like northern England, but it's a long time ago. Well, these two here with the lady standing, these are 2 vertical sets, okay? Then you have 1 horizontal set. How do we form this horizontal set, do you think? Remember anything about that? Do you remember the word exfoliation joint? Vaguely. Those are usually related to rapid erosion and high horizontal stresses due to the erosion, the glacier erosion in this case. And they are often with a high frequency close to the surface and then die out in the uppermost 100 meters. So exfoliation joints like these ones here, would probably not be found, say, at 500 meters depth. So be very careful to extrapolate your observation from the surface that has been eroded by glaciers down to great depth. The vertical ones would continue, but the horizontal one might very low density. Okay, we don't need to expand. This is just adding. You just add. You multiply by one set in addition to the other ones to get this. So it's not. You don't need to worry about it. Percolation threshold you need to worry about. Percolation threshold. Percolation threshold with this diagram is a common question, and that's because it's important. So I explain to you here. Percolation threshold is reached when there is an interconnected cluster of fractures between the points of interest in the rock body. Between the points of interest in the rock body. Between the points of interest in the rock body. We often call them point A and B, that's called X and Z. Between the points of interest. Percolation threshold is when there is an interconnected cluster of fractures, conducting fluids of course, between the points of interest in the rock body. Let me explain this diagram. If you look here, these are a lot of fractures, but there is no cluster from A or 1 to 2 or A to B. There's no cluster here connecting these two. Here you have a cluster of two. One up here from this point to that point, and another one going here and going here. So when you have no cluster connecting, the fluid flow is zero. The permeability is zero. You can have a lot of fractures, but if they're not interconnected, you can't have any flow through the network. So if you look here, the vertical axis is permeability. So until you reach the percolation threshold, the permeability is zero. Absolutely zero. There's no flow going on because you don't have any interconnection. You can have millions of fractures, but if they don't form a cluster, there cannot be any flow. Then suddenly you form a cluster. They could, for example, be here. There was only one missing link, and finally that little fracture connects to two others, and then you get to permeability, and it rises rapidly, and then levels out. That's the maximum flow that can go through this cluster here. This one. Percolation threshold means simply that you can have fluid flow from point A to B. Before you reach it, there is no flow going on between A and B. You can have all the fractures filled with fluids, but there is no flow. They're just there. Very important in bioindustry, very important in hydrogeology, everything you have to do with fluid flow. So percolation threshold, absolutely be clear about a popular question. And how do the stresses affect your fractures? We take a break soon. Well, it's very simple. If the fracture is perpendicular to sigma 1, or the maximum compression, it tends to close. No, they close never completely, but it tends to close, so the fluid flow is going to be less. As the crystals increase, fluid flow is less. If the fracture is perpendicular to sigma 3, and therefore part of the sigma 1, or sigma 8 maximum, it tends to open up, and the fluid flow is going to be greater. So here you see it very clearly. This fracture tends to close. This is simple logic. This fracture tends to open up. And we have tested this in places like Norway, and surprisingly, given that it is so simple, we can find that the fractures oriented parallel with the orientation of regional sigma 1, they tend to be more open than fractures that are perpendicular. But don't extrapolate too much because you have local stress fields. The current stress field can have huge effects on fractures. why does current stress field not have so huge effect on pores? Why does it have much more effect on fractures than pores? Why is the application of porous media in oil industry, where they say the stress doesn't count very much, why is that okay model, whereas the same model in the oil industry where there are fractures and they say the stress doesn't count is very wrong?
Because the pores are so much smaller.
They're much smaller, and what is the shape of them?
Circular.
A round or elliptical, and you need enormous stress to close or break such a shape, whereas you have often fractures that are maybe 5,000 times longer than they are open, so very easy to close. Okay, we have 5-6 minutes left, so I think we take a break now. Have a cup of coffee.
Yeah. To the power 3. Yeah. What was the power 3? You can pause it.